All right, we're looking at section 11.4, which is the comparison tests. So far, we know about p-series and geometric series. We know that p-series converge when p is greater than 1, and diverge when p is less than or equal to 1. We also know that geometric series converge when the ratio r, when its absolute value is less than 1, and it diverges if the absolute value of r is greater than or equal to 1. So what we're going to look at in this section is other series that aren't p-series or geometric series, but are kind of close to them, and we can compare them to either a p-series or geometric series and decide if they converge or not. Let's just start with an example, and then we'll state the test in detail. But let's look at this. What about this series? 1 over 3 to the n plus n squared. And I'll make n go from 1 to infinity. Now, this is not a p-series or a geometric series, but what I'm going to do is look at the dominant term on top and bottom. Now, the dominant term on top is 1, and the dominant term on bottom is 3 to the n. So I want to compare this with what we get if we just look at those dominant terms. When we do that, this series over here is geometric. R in this case is 1/3, so we know it's going to converge. We could figure out what its sum is, but I don't really care. At this point, all we really care about is that this thing converges. Now, let's compare the terms. If you look at the terms of this series, the one given to us here, if we look at 1 over 3 to the n plus n squared, and we compare that with 1 over 3 to the n, over here, this has a bigger denominator. And bigger denominator means it's a smaller number. So we get this inequality here. If you think about what this means, over here on the geometric series, we're adding up a bunch of numbers, and we know that converges to some finite sum. Well, over here, we're adding up a bunch of numbers, and we know that each of those numbers is smaller than the corresponding ones added up on the other one. So what this tells us is 1 over 3 to the n plus n squared is less than 1 over 3 to the n. This thing over here converges to a finite number. That means this over here has to also converge to a finite number. So this converges. Let's look at one more example while we're doing this. Suppose we have three to the n plus n squared over 2 to the n. Now, this is not quite a geometric series. If this n squared weren't here, that would be a geometric series. So let's compare it to three to the n over 2 to the n. This is geometric. R in this case is 3/2. That's bigger than 1, therefore this thing diverges. Now, if we compare the terms of this series over here are 3 to the n plus n squared over 2 to the n. The terms of this one are 3 to the n over 2 to the n. Now, over here, the n squared means that this has larger numerator. So larger numerator means larger number. So this is bigger. So what that tells us is this sum over here grows to infinity. And this sum over here is made up of adding up bigger numbers. So therefore, this one that we're given, 3 to the n plus n squared over 2 to the n, that has to diverge as well by comparison with this guy, which is a known divergent series. So we know this one adds up to infinity. This one over here has bigger numbers. Does that mean it diverges to something bigger than infinity? No. It means it diverges to infinity, but it does it a little faster than the other one. Let's look at the statement of the comparison test. It says if you've got two series with positive terms, if AN series converges and BN is smaller than AN for all n at least one, then BN has to converge as well. The idea there is it's smaller than something that's known to converge. That means it also has to converge. If AN diverges and BN is bigger than that, than AN for all n, then this series BN has to diverge as well. So let's look at some examples. Okay, this example 1, we've got 2 over n cubed plus 4. Now, what I'm going to do is compare that to 2 over n cubed. On these examples, I'm not putting in the starting point and the infinity on top. We can just assume those to be 1 and infinity. So 2 over n cubed, this is a p-series. And since p is 3, this one converges. And if we compare 2 over n cubed plus 4 with 2 over n cubed, this has a bigger denominator, so therefore it's smaller. So we have a convergent series here. This is a series with smaller terms, so therefore it also converges. All right, example 2. We would compare this to 4 over n squared plus 12n. This is not a very creative example because it's very much like the previous one. This is also a convergent p-series. And actually, that should go away. This is a convergent p-series. This has smaller terms because it has a bigger denominator. So therefore, the original series here also converges. All right, example 3. We could compare this to something, but before you jump straight in with the comparison test, you always want to do the test for divergence first. On this thing, if we take the limit as n goes to infinity of 3n squared plus 2n minus 1 over n squared plus 5, notice these are my dominant terms, and so this gives me 3. That's not equal to 0, so therefore this diverges by the test for divergence. I didn't write that out on the previous 2 examples, but I sort of mentally did the test for divergence on those, because on example 1 here, when n goes to infinity, this term goes to 0. And same here. When n goes to infinity here, the term goes to 3. So you're eventually adding up an infinitely long stack of numbers that are essentially 3, so it diverges to infinity. Let's look at this one. This is kind of similar to the others, but we have to figure out what to compare it to. If you recall, y equals inverse tan of x looks like this. And it has a horizontal asymptote over here at pi over 2. So we compare this to pi over 2 over n squared. I guess I should make this a sum here. And this right here, if you want to, you can pull the pi over 2 out front, but it's not really necessary. But this thing converges. It's convergent p-series. And so how do we compare these? Or rather, how do these compare? Well, inverse tan of n over n squared, if you compare that to pi over 2 over n squared, inverse tan is going to be less than pi over 2. So therefore, this is convergent. The original one was also convergent. Now, on all 4 of these examples, we sort of lucked out in that the inequalities went the correct directions. Notice up here, if the known series converges and your inequality works out, then the new series converges. If the known series diverges and the inequality works out, then the known series diverges. What if that inequality doesn't work out? Well, if the inequality doesn't work out, that's when you need to use the limit comparison test.